Okay, so in the last class we started out and we actually nearly finished the classification cost function, which which we discussed a lot in details. You can see here we have a lot of details available, and most of it were covered in our earlier lectures. So by now I think you will be aware of all the terms which are actually used in these expressions. So our next actually target is to basically see whether, just a second. Okay, so our next target is to see whether this cost function has any drawbacks or not. So we will check that now. And can anyone tell me the drawbacks of this cost function? Though we are using it, but there is a subtle drawback in this cost function also. Anyone, any idea? What can be the possible drawback of using this particular cost function? So basically the problem with this particular cost function is we have this argument which is inside this log function. So if you observe this particular sigma, which is the sigmoid onto the transformation x dot theta, if this value becomes close to 0, or it becomes 0 actually, then this particular cost function which we have defined will become undefined, because this particular term will blow up and it will go to infinity, right? So basically the problem arises when this particular sigmoid expression which becomes close to 0, then this particular cross entropy term which we are defining will not be valid anymore. Similarly, here if your this term becomes close to 1, then you can see 1 minus 1, again it is 0, then it's again a problem. So you can clearly see that at the extreme ends of the sigmoid, which is like this, at the extreme end on both the sides, this particular function will not be equal to will not be defined. So we will see how we can overcome this drawback by using another loss function, and which we are calling as Perceptron loss function. So today we will discuss another way of doing the classification through Perceptron algorithm. And Perceptron algorithm, we will define a different loss function which will not have these problems, like when your sigma is touching 0 or when your sigma is touching 1, this particular cost function is undefined. So we will try to overcome this by writing a different loss function which comes in the category of Perceptron loss function. And please note that this particular lecture will be formulated by group 6, and these guys have to submit this in the next class. So the deadline for that is next class. So note that. So this will be for group 6 here. So I'll write it here. So this is for group 6 now. So here what you can see is now we have this drawback, and we will try to overcome this drawback by using the Perceptron algorithm, and we will come to that in a while. But before going there, let me show you there are few ways of solving this. The first way of solving this problem, which I was telling you that it is touching close to 0 and 1, the first way of solving it is through using of regularization. So remember, we have dealt with a lot of regularization thing in our linear regression problems, where we have used a regularization parameter for our linear regression. If you recall, we have derived a lot of expressions related to that. Similarly, you can do this similar analysis on the classification setting, and here you can see we are again writing this extra term, which I think you must be aware of now, because we have included this setting earlier also in case of linear regression, and we have actually used multiple ways of regularizing by using L2 or L1, but right now I am keeping it simple here, and I am using only L2 regularization. So you can see here what I am doing is I am appending an extra term which is over here along with the original cost function which is over here. So what happens is when you use the regularization, that is when you penalize the coefficients of the model, that is thetas, then what will happen is it will try to adjust these values of sigma, and it will not allow it to go touching 0 or 1. So somewhere it will help you out in avoiding this type of situation where you have this blowing up of the problem, like here you have close to 0 and close to 1 situation, right? So what happens is it tries to adjust the values of theta in such a way that this problem or this situation will never arise where this value will be equal to 0 or this value will be equal to 1. So it helps in actually regulating the cost function which is given over here by properly but by avoiding that situation where these values will close to become 0 or 1. So it helps in avoiding it. Another help which we get by regularization is that it helps in overfitting. It helps in reducing the overfitting. So we have already discussed about this overfitting problem in case of linear regression. Same goes here for the classification setting also. So if let us say you are using a large number of features which involve x1, x2, x3, x4, or maybe the polynomial versions of of your features like x1, x2, x1 square, x2 square, x1, x2. So what happens is if you use a multiple number of features, it might be the case that it will lead to overfitting of the boundaries. So here if you see, this is a very simple example I am trying to show you over here where we have two features only, but I'll just try to show you the concept that what overfitting is and how regularization is trying to avoid that. So if you try to use multiple features that involve x1, x2, x3 or x4 or x1 square, x2 square, something like that, then what will happen is your boundary will become very complex and it will try to classify each and every point to either class 0 or class 1. So like for here in this example, if you use large number of features, it might be the case that your boundary will become like this. It will try to classify each and every point into either x or 0. So here you can see the training error is almost 0 because you can see all the points are properly classified and your boundary is highly nonlinear, and nonlinearity is coming because you are using large number of features and each and every data point is correctly classified. So what you can say is your training error is equal to 0. So let us see whether this particular situation really helps us or not. So now let us say you have a test set from where the test examples are this and this. So these crosses which I am putting over here, if you see closely, then these crosses are actually coming from the same distribution where you already have these x's around. So it is coming in this same distribution which I am highlighting over here. So your x's are in this same vicinity of x's which are already there in purple shape. So we are not saying that your testing samples of x are here or here. What we are saying is your x's are close to the original purple x's which are there. So right, we are not saying that your x's are too far from the normal distribution which you have here, but we are saying our x's are close to the original distribution. But now because the boundary is so complex that these x's, though it belongs to this particular class, but it will be classified as 0, or let me call this as 0 class, and let me call this as first class 1. So though we have these x's in the vicinity of the original distribution of x's, but because the boundary is so complex that these x's will be now classified as 0, as you can see clearly that all the things which are on this side of the boundary are classified as 0, and all the things which are on the left side of this boundary are classified as 1. So this is the problem because of which overfitting occurs. So here in this particular situation, your training error, though it is 0, but your testing error will be some value. There will be some value here. So this means it is not allowed at all. This type of situation is not allowed because the generalization is not happening properly, because if you put some more samples here, then the more sample means these new samples, then the machine is not able to generalize to these new samples as they are treating it as an error. So now what happens is, in order to avoid this, what we are doing is we are using regularization. So regularization actually helps us in relaxing this boundary which is too complex. So what happens now is our new boundary might become this. Let me draw that with a different color. So let us say our new boundary becomes this. This is our new boundary. Our earlier boundary was green and now our new boundary is blue. So if this is the situation where your new boundary is this one, you can see that we have training error already, because this 0 is not counted in this class. We have missed that 0 and we are saying, let us say that this 0 is belonging to X. So that means in this particular situation, the blue situation, we have some training error. We have some training error, though it is small, but we will have some training error, no problem. But you see now, the new samples which we are incorporating over here, they are all treated as class 1 samples. They will not be treated as class 0 samples, because this boundary, though it is making error on the training samples, but the testing samples, the training error is small, because it is giving you, for the new samples, it is generalizing it properly and it is saying, okay, all these new samples which are inserted, they are all crosses. So that means your testing error will be small. Here your testing error is big. So this testing error will be small compared to this testing error. So what it means is, your regularization actually reduces the training error as well as the testing error to a very small value. This is allowed. But this situation is not allowed, where your training error is exactly 0 and you have some testing error. So we try to use regularization to reach to this situation where your training and testing error are there and they are much smaller compared to having 0 training error and high testing error. So we do not want this situation, we want this situation. So basically regularization actually helps you in achieving this problem by reducing the overfitting and making a curve which is a little bit relaxed compared to the situation where the curve is highly complex. So this is the first way of using regularization, and these are the gradient descent equations that you can derive yourself for this particular cost function, which is over here. So what it is doing is, it is actually calculating partial loss by partial theta for this particular loss function. You can calculate now yourself, it's very easy to do it. So here you have the expression for theta 0 and this is the expression for theta j, and you can code yourself and derive these equations and do the gradient descent. Now I think you are pretty confident in the contents. We have already done similar type of thing in linear regression. You can do similar thing for your logistic regression also. Now comes the part which we are calling as using perceptron. So perceptron will actually try to avoid this situation where you have this problem which I was telling you, that if this is going close to 0 or this is going close to 1, this particular loss function will not be valid anymore. So what we do is we try to actually come up with a different cost function which we call as the perceptron cost function, and the perceptron cost function is defined like this. Here if you see, what we are doing is we are having this original hypothesis function. This is already this is the hypothesis function that is generated by the machine. So what we are saying is, if this is greater than 0, we are calling it as class 1. If this is less than 0, we are calling it as class minus 1. So note that right now I am using labels 1 and minus 1, I am not using 1 and 0. So as I told you last time also, if you use 1 or minus 1 or 1 or 0, both will work fine. The only thing is the expression will change a bit. So here right now I am using 1 and minus 1, and we will try to see that the derivation that we will get for this particular loss function will coincide with the loss function that we have derived for the classification setting which we had done last time for labels 1 and minus 1. So if you remember last time, for the classification we were doing for two different labels the derivation. The first derivation was when the labels were 1 and 0, and the second derivation is for labels 1 and minus 1. So here also we are keeping labels as 1 and minus 1. So what we are saying is, if the hypothesis function, or you can say the result of the machine, if it is giving you greater than 0, we are calling it as label 1, and if the results are less than 0, we call it label minus 1. So this is quite analogous to the to the coordinate geometry if you have studied it in your in your earlier courses. So what happens is, if you want to know which point is lying onto which side of a line, what you do is you actually put that point onto the line equation, and if the line equation gives you a value greater than something, then we say it is on this side of the line. And if the point, if you put that into the equation of the line, and if it gives you a negative value, then you are onto the left side of the line. So basically it's a simple coordinate geometry rule only, where we put some value in this equation of the line, because x dot theta is actually the line, the training the decision boundary. So if you put some value and that value comes out to be greater than 0, means your yi is 1, and if it is less than 0, your yi will be minus 1. So it is basically defining the concept, and I am drawing the analogy with the with this particular coordinate geometry thing. So this is quite easy, and there is no actually, I think, thinking required here. So, and now the thing is, as I told you last time also, that if I want to combine these two equations together, how we can do that? So it's very easy. We will define a function which looks like this here. So here you can see the loss function, a new loss function now. Earlier the loss function was different. We tried two different loss functions last time. This is the third loss function which we are defining for the classification setting. And here you can see what we are doing is we are actually summing the values from 1 to m, where m is the total number of samples, and then you are taking max of two values, 0 and yi times xi theta. So what I am doing is I am actually multiplying the labels with the corresponding hypothesis function. So this is the hypothesis function which is actually generated by the machine. So we are actually multiplying it, and we are putting a minus sign here. Now the advantage of using this particular loss function is that there is no log term involved, and we will not run into plus minus infinity situation, as I was telling you in the earlier earlier setting, where you have plus minus infinity problem coming up because of this loss function which is given over here. So this loss function problem is avoided by using a new loss function which is given over here. So let us see what this function is all about, and how we are trying to use it in our perceptron algorithms. So so let us do one thing. This is already, this is x dot I theta. So what I am doing is actually, if you remember, x dot is nothing but it's a appended one in the matrix. So if you go to our linear regression definition, from where we started out with putting x dot, which is one appended in the columns of the matrix X. So what I am trying to do now is I am actually separating 1 with x differently. So if I separate 1 and separate x, then I can write it as this equation also. So here you have xi times theta plus theta 0. So theta 0 has 1 attached to it, which is basically the one attached to the labels. So one attached to the features x. So 1 is now with theta 0. So I am writing it differently like this, and what it is basically, it is nothing but we are calling it as g theta x of I, a new terminology which I am trying to pose here. So this g theta xi is nothing but it's a xi theta plus theta 0. So let me let me write this expression which is given over here with this expression. So here you can see x dot I theta, I am replacing it with g theta xi, same thing. So now what we want to see is we want to understand this cost function, that what this cost function is all about. Basically it's a loss. So if you observe our binary cross entropy function also, I explained you the loss function for that, and if you recall what we explained you that if the labels are 1 and if your machine is also generating a value close to 1, then the loss function given by the binary cross entropy will be close to 0. And if your labels are 1 and if your machine is predicting 0, obviously the loss function will be much high, and I derived it last time for the binary cross entropy. So we are trying to show you the same thing here also, same logic. So here what we will see is if your decision is correct. So if our decision is correct, then we want to see how much loss we are actually getting if our decision is correct. So our decision is correct in two ways. This is the decision which is coming from the machine, and this is the decision, this is the already known value of the labels. So if your machine is giving you a value greater than 0, and if your labels are also +1, that means you are making a correct decision, because machine is giving a value greater than 0, and we already told that if the results are greater than 0, we will say that its label is 1. So here the decision of the machine and the decision that your labels are giving are equal to are same polarity. Similarly, if your machine gives you a value of less than 0 and your labels are also -1, then also our decisions are correct, because we know that if the machine is giving a value less than 0, then the labels are also less than -1. So both of them are right. So in both the cases our decision is correct. So if you multiply this with this, as you can see here, both of them are multiplied. So if you multiply both of them, the result will be greater than 0. You can see here, this is also 1, this is also 1, multiplying both will be greater than 0. This is less than 0, this is also -1, so multiplying both of them will again be greater than 0. So this is actually always greater than 0. So if you take the loss function L theta, which is max of 0 and this particular thing, which this one you already know it's greater than 0, then minus value will be always less than 0. So the max of this will be 0. So you can see if the decision is correct, if your decision is correct, then your loss is 0. That is what you actually want from any classifier, because if the decision is correct and if you have a high loss, then there is no point in having that classifier. So this is important, that whenever your decision is correct, the loss function should be 0. This is quite evident and it can be seen from this equation also. If the decision is wrong, means your machine is giving a value greater than 0 and your labels are -1. So these both are different, and here your machine is giving a value less than 0 and your value of the label is greater than 1. So in this situation your decision is wrong. So if the decision is wrong, you can multiply these two together and you will get a value less than 0. So if this is less than 0, this thing is less than 0, then what you can observe is that if you take the max of 0 minus of yi g theta xi, then what you will get is plus yi g theta xi, which is greater than 0. Because this particular thing will be greater than 0, because this is already negative and negative of negative will be positive, and so whatever value of L theta will be, it will be plus yi g theta xi, which is greater than 0. So you can see now that when the decision is wrong, the loss will be proportional to this multiplication, which is yi g theta xi. So this is basically when the decision is wrong. So this is basically the cost function intuition which I have defined here. If anyone has any question, they can ask, otherwise I will move again ahead. So this is the loss function definition. Any questions here related to this? So okay, so now once we have this, let us compare the loss functions which we had earlier. So this is basically a linear regression cost function which we already had last time. You must have seen this. The properties of this are that it's a convex, it's a closed form solution, and it's having a unique global minimizer, which we have already seen so many times. Then we have logistic regression, which is given over here. This also you have studied and you saw that it's a convex function, but it is not having any closed form solution, because as it was in the case of linear regression, your answers for the closed form solution was x transpose x and all that stuff which we had, right? I forgot right now, but we have that closed form solution for estimate of the theta hat. So this closed form solution is not available here in case of logistic regression. And it also has a unique global minimizer, because this particular loss function is a convex loss function, which we have already discussed. Now comes the perceptron algorithm, which we are discussing now. So we have discussed this particular algorithm this side. You can see here it is also called as soft perceptron. Why we are calling it as soft will be known to you now in a while, but this is the function which we are calling as soft perceptron loss function. It is also convex. It has no closed form solutions and it has a unique global minimizer. So this is the property of the soft cost function that we have over here. And if you want to go for a hard version of it, then what you do is you apply a signum onto the machine hypothesis function. So signum function, you know, it's already -1 to 1. So you can see now, if you remember last time also we approximated the classification decision boundary by using a signum function which is -1 to 1, and then we went for the relaxation of this by using a tan hyperbolic function, which is the softer version of the signum. Same thing applies for the perceptron also. That is, if you use the hypothesis function itself, then it's a softer version. But if you apply signum function on this, then it becomes a hard function. And the problem with using this hard is similar to the problem that you had with the signum function in the classification setting. That is, it is not convex and there was no closed form solution, and many global minimizers will be there, because this signum function will create problems and you will have multiple flat minimas. If you remember the cost function that I have shown you, it had multiple flat minimas, and you can settle down to any one of them, and the global minima was not there. So this signum function will create problems. So this is the softer version of this signum function. So this is basically the hard perceptron concept. This is the soft perceptron concept. But we will mainly focus on this softer version. So if you remember, maybe I don't know whether you know it or not, this ReLU expression is normally called as max of a comma 0. This ReLU is actually, the term which is normally used in deep learning. I don't know whether you have studied it or not, but it is basically used in machine learning, in deep learning area, and ReLU is basically defined using max of a comma 0. So here you can see we have max of a comma 0. Just a second. So ReLU is another unit which is normally used in the deep learning architecture. I am not going there. If you want, you can study from the books, but the ReLU is defined for this particular mathematical expression, which is max of a comma 0. So if you contrast it with the perceptron cost function, the perceptron cost function is max of minus a comma 0. So this particular thing is actually a. So what I am saying is minus of a comma 0. So basically the importance of showing this slide is that ReLU is nothing but it's a mirror image of the perceptron loss function. So basically, this particular ReLU concept has not come just out of bloom. It has come from the motivation of using perceptron loss function. So they have taken the motivation from here and taken the mirror image of it, and this slide is showing you that. So this is the relation between a ReLU and the perceptron loss function, which is given over here. So now if you see the perceptron algorithm, this is the softer version of the perceptron algorithm which we are discussing, and this is the hard version of the perceptron algorithm which we have discussed, which we are not discussing, but this is the one. So what is our strategy? Our strategy is actually, our aim is to actually solve for this harder version, but because harder version is the is the close to the ideal situation, because if you do a classification, this classification is best because it's a ideal situation, but we cannot do that. As you know, the differentiability is a problem at this location. So what we do is we approximate it with tan hyperbolic function and do the adjustments. So this is basically an approximation to avoid the differentiation. So but our target is actually to solve L hard problem, which is this one, but we cannot do it because of the differentiability problem here of the signum function. So what we do is we use gradient descent on the softer version, which is the one which we have over here. So if you recall our proximal gradient descent idea which we had discussed last time, you know that we discussed that the loss function is not differentiable at a specific point. So the solution was to come up with a proximal function which is a convex as well as the differential, and then we can go slowly to the point where the function is not convex, and we will settle to the point which is the global minima. So if you recall, similar thing is happening over here. What we are doing is we are actually trying to go gradient descent on the softer version, and what we know is it can be shown easily that the solution that you obtain for the softer version, that is the theta star that you will obtain for the softer version, satisfies the hard version also. So this I will leave as an exercise for you people to go and understand that how it is possible, but it can be easily shown that the gradient descent, if you do on this loss function, then the point that you will get, which is the theta hat, will actually satisfy this hard version also. So this is basically the idea, like we will be using gradient descent on the softer loss function, and what solution that we will get actually satisfies the harder version also. So that is the proof that you have to do yourself. So we are defining the loss function again here. So I am writing this loss function like this, and you can see now there is a problem because you have this max operator. So max operator again is a non-linear operator, and it can create flat surfaces in the cost function similar to the signum function, and it will also be a problematic situation, because if you have flat situations, your algorithm can initialize at that point and stop over there itself. So we want to avoid this non-linearity which is available here. So what we say is we can write this expression as this expression which is given over here. And remember now that your I is actually running from 1 to m, which are m are the total number of samples in the data set. But now here the I is actually I is actually belonging to the set m theta, where m theta are the set of misclassified samples. So if your m theta is basically a samples of misclassified data points, so basically what we are doing is we can reduce this max will be gone, and your expression will be like this if you consider only the samples which are in the misclassified samples. So if you only focus on misclassified set, and if you sum all the data, you will be only summing up yi's corresponding to the g theta xi's, and there will be no max involved, and you can solve this loss function easily. So let us see how we can do that. So I will try to prove that these two are equivalent. So if you see here, what we are trying to show is that the left side of the equation is same as the right side of the equation, which we will try to prove now. And note that here I is actually belonging to the set m theta, and here I is actually running from 1 to m, which is the complete sample space. So if xi is misclassified, so the sample which is misclassified, suppose, then you can say that this particular sample which is misclassified will be in the set m theta. So m theta is basically the set which contains all these misclassified samples. So if xi is misclassified, it belongs to m theta set. So in this case of misclassification, if you recall, then the sign of the hypothesis function will be opposite to the actual label of that sample, because it's a misclassified point. I have discussed it in the previous slides also, that if you have a misclassified point, hypothesis will be of having different sign with yi. So the multiplication will be less than 0. So if the multiplication is less than 0, the minus sign if you take, then the inequality will reverse and it will become greater than 0. So if you take max of either this or 0, it will give you this answer. Because this particular is greater than 0, so this particular expression is greater than 0 and this is less than 0. So if you take, equal to 0, so if you take max of either of it, it will give you the answer as this. And note that if xi is misclassified, your answer is this. And if your x is correctly classified, in that case, the hypothesis function will have same value as yi. So if the value is same, like this one is same as this yi, then what will happen is the multiplication of this with this will be greater than 0, because both of them will have same polarity. And if you take minus, then it will become less than 0, because the inequality will be reversed. And now when you take max of this comma 0, what you will get is 0 as the answer, because this particular expression here will be less than 0, and if you take max of less than 0 comma 0, you will get 0 as the answer. So if it is correctly classified, your answer is 0, and if it is not correctly classified, you will get this as answer. So now, keeping these 2 points into mind, if you expand the term which is on the left side, which we were trying to make equal to this, see that this, you are trying to make this equal to this, right? So now I am focusing on this one. So if you sum this into 2 parts, the first part is that all the points which belong to m theta and all the points which do not belong to m theta. So these 2 points, these two expressions can be summed up. So when you have all the data points which belong to m theta plus all the data points which do not belong to m theta, if you sum them up, the total will be I running from 1 to m. So we are divided into 2 parts. In the first part, you know that if you do this summation, your answer will be equal to this. This we have already derived. And if your samples are not in the misclassified points, that means you are actually correctly classifying that points. In correct classification, you know this will be reduced to 0. So both of them are there, right? So this is here and this is 0. So now the expression that is left is this expression which is given over here. So you can see now we have proved that this expression which is given over here is equivalent to this expression which is over here. And now max is also gone, which is a trouble. So the non-linearity is also gone and you are left with these samples. So note that perceptron algorithm basically works with the misclassified data points, and this is the algorithm which is basically used to optimize the boundary. So this will be the loss function which we will be using for our perceptron algorithm. But the summation I will be focused on all the misclassified points. That is important. You cannot take all the data points. This particular loss function will focus on all the data points which are misclassified. As you can see, the loss function which you are using here is actually valid for misclassified points which are lying in the set m theta. So the perceptron algorithm, we will see that now. So this is the loss function actually, and what you have to do is you have to take the loss function's derivative with respect to theta, which we are already doing so many times, and then what you have to do is you have to come up with the new theta k plus 1 as old theta minus the alpha times the derivative of the loss with respect to theta. So basically you have to use this gradient descent. So the perceptron algorithm basically now is defined like this. So here you can see the perceptron algorithm is defined like this. So it is nothing but this expression only, with the derivative of the loss with respect to theta is nothing but this expression, and this is alpha, which is the learning rate. This is the old theta and this is the new theta. Sorry, this is the new theta and this is the old theta, and this is with the subscript j, where j is running from 1 to n. And for the bias term theta 0, we are keeping it separate, so it's theta 0 here. So the important point to be noted here in this gradient descent equation is that this is the step size, or you can say learning rate, and mk, which is over here, is the misclassified data set. So all the samples which are misclassified, then only you will be applying this gradient descent on that. So basically it's a misclassified set, and note that this misclassified set is subscripted by a value of k. So k is nothing but it's an iteration number. So this set will keep on changing with the iteration. So I will show you the diagram also, but note that this particular set, which is called as m subscript k, this will keep on changing as the data set changes, because as the iteration changes, the boundary will change, and with boundary changes, some of the points which were earlier misclassified will become classified, and some of the points which are earlier not classified properly will become misclassified. So it will be a problem. So mk will keep on changing as your iteration changes. So I will show you how it is doing, but basically mk is the set of misclassified set. So if you want to prove this equation, it is very simple. The only thing that you have to do is you have to take the derivative of the loss with respect to theta for this expression. So if you want to see that, it's very easy, right? So this is the expression for the gradient descent, and for L soft, I can write this expression which we already done. And now if you want to do the derivative of this particular part, this is nothing but this, and it can be bifurcated into two parts, where I belongs to the sets misclassified set, and when I do not belong to misclassified set. So if I do not belong to misclassified set, at that time it is 0. When I belongs to misclassified set, you take the derivative of the theta with respect to the hypothesis function, because there is no theta involved in yi, which is the labels. And then you know that if you calculate the derivative of the theta, which is a vector actually, so if you take the derivative of this with respect to the hypothesis function, you know that this theta 0 will be 1, which can be represented in the matrix form like this. And if you take theta with respect to this theta transpose xi, what you will get is the corresponding xij outside. So the j is the feature corresponding to theta j, for which you are taking the derivative. So basically it is basically calculating the theta for a specific theta. It is calculating the derivative with respect to a specific location of theta, and for that location the corresponding xi will come out. That's why the subscript with j is coming out here. So now you have this expression, which is the derivative of the derivative of this cost function with respect to theta. So this is over here, and you can plug it back into the equation, and what you will get is this. So in this you can see the theta 0 corresponds to the theta old plus alpha times yi. So this is basically corresponding to theta 0, and then for all other values of theta you will have this expression. So that is why you have this here, and you can combine these two in a matrix form, and what you will get is this expression which is given over here. So this is the gradient descent for the perceptron algorithm, and you can see now all the samples I actually belong to the misclassified points. They are not all the samples which are in the data set, but they are only the points which are in the misclassified data points. So you cannot do gradient descent for all the points. You have to do it on for the misclassified points also. So let us see a pictorial representation of this particular equation. So if you have any questions related to it, you can ask. Otherwise I will move to the pictorial illustration of how this algorithm is actually working out. Any questions here related to this? So if you have no questions, so pictorial representation actually shows you how this algorithm is working, so how gradient descent is working. So basically if you see here, we have data points which are blue data points this side, and then you have this purple data points here. So what I am saying is, I am calling this as label 1 and this as label -1. So note here I am using 1 and -1 label concept, not 1 and 0. You can use 1 and 0 also, but for this I am using 1 and -1. So here you see, if I am using 1 and -1, then you can clearly see that the decision boundary will be like this. But note that there are some purple points which are here, which are misclassified, because you have initialized the decision boundary here to start with. So it might be the case that these 2 points will be misclassified points, because they are actually with the value of y equal to -1. But right now they are classified as y equal to 1 because it's lying on the left side of the boundary. So our algorithm will actually focus on these misclassified points, and it will not focus on these points which are correctly classified. As you can see here, that the I value is actually depending on the misclassified points. That's why we will focus on misclassified samples. So what happens is, pictorially what is happening is, actually, this theta, you can prove yourself that this theta, which is the vector corresponding to the gradient descent, the theta that we will be using, the parameters, if you take the vector, it is perpendicular to the hyperplane, which is this one. This you can prove yourself. I am giving you this as an exercise, that this theta k is actually perpendicular to this hyperplane. You have to prove yourself. So this is normal to the hyperplane. So here what we do is, we connect this point to the vectors x1 and x2. So once you connect these points to the x1 and x2 vector, then what happens is, if you recall this expression, so you can see it is actually multiplying the label yi with xj. So if you see, you are multiplying yi with xj. So when you multiply yi with xj and you take the minus sign, so this is the vector xj, this is the vector xj, and what you are doing, you are multiplying it by y. So when you multiply it by y, which is minus, then what will happen is, these vectors will flip around in direction. So this vector actually flips and it becomes this vector, and this vector flips and it becomes this vector. So once you have these flipped vectors, now what you are doing, you are actually summing up all these yi's x's. You are summing up all these multiplications. So summing up all these multiplications means you are actually summing up the vectors which are over here. So if you sum these two vectors, it might be the case that the new vector will be like this. The new one will be like this, which is actually summing up these two vectors. So this is the new vector, which is focusing on the misclassified points which are over here. So the new vector along with the old theta k will give you a new vector theta k plus 1. Why it is like that? Because this is the old vector theta k and this is the new vector which is coming up because of the misclassified points. What you are doing, you are actually adding these two by weightage alpha. So you can see you are actually multiplying with alpha. So what happens is, you can multiply this vector by alpha. So that will actually make this vector a little bit small, because alpha is normally in between 0 and 1. So it will make the vector small. And then you are adding this vector with the old vector which is theta k. So if you add these two vectors, it will give you a new vector which is theta k plus 1. So if you see here, this is the new vector which is theta k plus 1. So now this is the second, this is the iteration which is going on. So now the new theta k is this, and you know that the boundary which is created and the theta are normal to each other. So when the new theta k plus 1 is like this, your boundary will actually shift to make it like this, Boundary will be now 90 degrees to theta, as a result of which your perceptron boundary will also shift in the anti-clockwise direction. So the new boundary will actually become like this. And this boundary actually has this as the theta k plus 1 normal to this particular boundary. And now you can see, if this is your new boundary, you can see these 2 points are now correctly classified and they are labeled as y equal to minus 1. In the earlier case, it is y equal to 1 here. So now this boundary is actually able to correctly classify them as y equal to minus 1. So this shows you the one iteration of perceptron algorithm, that how it is moving from here to here. So the important point is that this algorithm will actually focus on all the misclassified points. So the property of this particular thing is, this algorithm is that it's a non-unique global minimizer. So you will get a global answer, but it will not be unique, because if you see you have these data points and if you have these data points, what will happen is either of these situations can be your answer. So either of these curves can be your answer to the classifier. So it can be this also, it can be this also, it can be this also, it can be this also. So depending upon your initialization. So if your algorithm is initialized like this, then it might be the case that it will settle on to this particular boundary, or if your algorithm is initialized here, then it might be the case it will settle down to this boundary or this boundary, this boundary or this boundary or this boundary. So there is no unique answer to this particular algorithm. So the cost function, if you look, it will be something like this here, where you can have any answer to this, because it has a global minima, but the solution can be any point, and corresponding to each of these points you will have different answers of these curves. So the curves will be different based on the points where you will get this global answer. So this is the important property of the perceptron algorithm, that is, your boundary will not be unique. And the second important thing that has to be taken care of here is that this particular algorithm works only when your data is separable. That is, this data is separated from this. If this type of data is there, then it will work. But if the data that you have is like this, let us say, like you have this type of data, in this type of data it will not work at all. In this type of data it will try to oscillate. The boundary will always oscillate. By oscillation means your first iteration your boundary will be like this, in the second it will be like this, in the third it will be like this, in the fourth it will be like this, fifth it will be like this. It will try to always find out the points which are misclassified, and you can see here it will not be able to find out the misclassified. It will not be able to find out a solution where you will get all the blues at one and all the red at one side, because it's a non-linear boundary, and this is basically a linear classifier. Perceptron is basically a linear classifier. So this particular type of problem, this particular type of data set cannot be handled by a perceptron algorithm, and it will always oscillate and find out the solution for you, but it will not be able to converge to the final solution because your data set is non-linearly separable. So the perceptron algorithm always works for linearly separable data. It never works for these type of data. So this is the second point that has to be kept in mind for perceptron algorithms. Any question here related to this discussion? Are you able to follow?
Yes, sir. Yes.
Okay.
Yes, sir.
Okay, so once it is done, what we can do is now, there is another way of solving this max problem. So you remember last time we removed this max which was here. If you remember, we tried to remove this max by using this expression, and the main objective was to remove this non-linearity which is available here. So similar thing can be done, like you can remove this max by using the approximation of that, which is this. So here you can see now, if your max has different arguments like s0, s1 till sc minus 1, then you can approximate it with log function with exponentials raised to the s0, s1 till sc1. So this you prove yourself. I will not prove it. I am leaving as an exercise for you to prove that max of this is nothing but log of this expression. So here, if you see pictorially, the max operator which we were discussing, this is the max operator, right? Max of minus a comma 0. So we are trying to see, earlier we removed this max with some other concept which we discussed just now, and the main objective was to remove this differentiability problem which is at here, because it is not differentiable at this point. So we removed it by using the earlier approximation which we had done just few slides back. So similar modification can be done by using the softer approximation of max, which is this one. So this is also called as soft max. Why? Because you are actually making a softer version of the max operator, and the softer version is this version. You can see now it's a soft version, and it is differentiable at each and every point. So this dotted lines are the softer version of the max operator, and this is the one which is you can write it using this expression. So now if I want to write this expression in terms of the log, it is very easy, right? This is s0, this is s1. So what I am doing is I am actually writing this g theta xi with this original definition which we had started out with. So now this is your S0, this is your S1. So what I'm doing here is, this is your e to the power s, or maybe this is your S0, this is your S1, then this is basically e to the power S0 plus e to the power S1. So you can see now this S1 is basically e to the power this one, and this S0 is nothing but e to the power 0. So once you have this expression, which is the softer version, so it has to be like this, approximated, not exactly equal to 0. So once you have this, you can see now that e to the power 0 is 1, and this expression is this expression with dot now. Earlier there was no dot, but now I am just representing it in a compact fashion. So you can see now the max is replaced by this softer version, which is over here, and this is basically nothing but it's a soft max. So now if you recall our earlier lecture, let me go to that lecture. So if you recall here, this is the slide where I was telling you that it is a soft max cost function. It is called as a soft max for the logistic regression, and I told you like why it is called as soft max will be answered later on. So now you recall that this loss function, which is a soft max loss function, this is same as the one which we are discussing here. If you recall, both of them are same. And note that this classification example which we had taken, or the loss function which we had derived for this, it is for labels. It is for labels +1 and -1. So for that you are getting this loss function, right? Similarly here also, in this particular perceptron setting also, I have taken labels as +1 and -1. That's why I am getting the same answer for the perceptron also as the same answer for the classification setting also. So both answers are coming out same, and the idea was to show you that both of them are coming out to the same point. And the important point is soft max, it is called because it is approximating the max operator by a softer version. That's why it's called as a soft max. So this is basically the intuition behind using the perceptron algorithm, and now you can easily see that this perceptron algorithm also coincides with the derivation when you use the classification algorithm with labels +1 and -1. So both of them converge to the same solution. So names are different, the way we are treating them are different, the loss functions we are taking them are different, but at the end they are converging to the same solutions. So the perceptron algorithm can be written in this way also, that is, you initialize the values of thetas to a value of 0, 0, let us say, because you are initializing some variables. So I am taking 0, 0 initial, then I am running for I equal to 1 to some iteration. So I am taking some iterations, maybe 10 or 11, whatever, and for all these iterations what I am doing is I am taking all these samples first in the data set, and for all that samples what I am doing is I am actually first formulating the hypothesis function. This is nothing but, this expression is nothing but it's theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. So we are actually writing the hypothesis function, linear hypothesis, not non-linear. So you note this, it's a linear hypothesis function. So you can see now we are writing this in a compact fashion like this, and I am calling it as g theta xi. And now what I am doing is, for all these data sets, all these data points, I am only focusing on the points which are misclassified. So as I told you that this algorithm works only for misclassified points, so you can actually test that misclassification using this particular condition, which is when you multiply the label with the hypothesis, it will give you a misclassified answer which is less than 0. Then you can clearly say that the point which you are considering, which is xi, is a misclassified point because this answer is less than 0. So once this condition comes out to be true, then you can use these gradient descent equations which we have derived earlier just before here. If you recall, these equations are these equations. So you have to use these equations to update the values of theta 0 and theta j. So once you do all this for all the misclassified points, because you have to do it for all the misclassified points, your theta j and theta 0 will come out to be some value. Once it is done, that values are the estimated values of your theta, which you can plug in into the hypothesis function to get the correct hypothesis, or maybe the machine generated decision boundary, because this theta hats will be all coming out from this algorithm. So this finishes off with your perceptron algorithm, and the pros and cons of the perceptron algorithm are, as I have told you, it's a simple algorithm, but it will only deal with two classes which are linearly separable. As I told you, if they are not linearly separable, your boundary will oscillate and it will not give you the final answer. And second problem is that the decision boundary is not unique, which I have already told you, that there will be multiple decision boundaries depending upon where you start, and there might be a situation that your boundary comes out to be like this, and this boundary is not good boundary because you can see here that it is touching this data point. So if the boundary shifts a bit, or maybe if the noise enters into this data point, then it might be the case that this point will shift to this side, and if this point shifts to this side, then what will happen is this boundary will say that this is actually belonging to this class, though it is actually belonging to this class. So this type of boundary is not a good boundary. This is the good boundary because it has margin available for these points and these points. So by saying margin means if this boundary actually shifts a little bit like this, still it will be able to classify these points accurately because there is a margin of these boundaries with these points. So we will understand how to overcome these problems which we have discussed here, that is, decision boundary is not unique, and the decision boundaries always touching one of the data points can cause problem in robustness. So these problems will be discussed in our next lecture when we will discuss support vector machines. So these 2 points are actually acting as a motivation for you to enter into this topic, which is support vector machine, which addresses these 2 problems. If you have any questions, you can ask. Any questions?